Section 4 of Chapter 25 now leads us to Faraday's law, which is basically expressed by an equation that relates the changing magnetic field or changing magnetic flux and the EMF that it induces. So let's talk about that. Okay, so first, let's recognize and remember that we notice a changing magnetic flux causes an induced electromagnetic field. To remind you, we had a loop that had no current in it, but it was connected to a current meter. And if there was a magnet that was moved toward or away from it, or into it, or out of it, we noticed that the needle on the current meter deflected, indicating that there was a current induced in the circuit. And that induced current had a direction which was either clockwise or counterclockwise based on whether the magnetic field was increasing or decreasing. That connection can be understood best by Lenz's law. We can determine the direction of the induced current based on Lenz's law, which we just got finished studying. So, once we acknowledge that an induced EMF is always associated with a changing magnetic flux, the induced current by Ohm's law would be the EMF divided by R. So a circuit that has resistance R would carry a current I when the EMF script E is induced by a changing magnetic field. So whatever the induced EMF is and whatever the existing resistance in the circuit is, those two help us determine then that current is in fact relatable using Ohm's law as script E over R. The induced current is the EMF divided by the resistance in the circuit. Now the direction of the current, as we've already stated, is determined by Lenz's law. And Lenz basically says that the current will be induced such as to produce a magnetic field that opposes the change that produced the current in the first place. Let's rephrase that. When a changing magnetic field causes an induced current in a closed circuit, say, for example, the magnetic field is increasing over time across the loop, the magnetic field that crosses the loop of the, or the area of the loop, the circuit loop. If the magnetic field is increasing in time, then the EMF is going to be induced in that loop such as to produce a magnetic field which points in the opposite direction to try and slow down or change the increasing magnetic field. So it always develops a current that produces a magnetic field that opposes the change that's producing it. It doesn't always oppose the field, it opposes the change. So for example, if the field is decreasing in time, then the induced current is going to produce a magnetic field which is parallel to the outside field to try and strengthen it, to try and slow down its decrease. Now, the size of the induced EMF is now something that we can determine using Faraday's law, and so let's talk about that equation. Faraday's law basically says that the strength or size or magnitude of the induced EMF is the rate of change of the magnetic flux through the loop. In other words, there's a mathematical equivalence between the two. Faraday's law says that the magnitude or strength of the induced electromagnetic force is equal to the rate of change of the magnetic flux through the loop. Okay? That's expressed down here by this equation. This is basically the expression of Faraday's law. What is delta phi over delta t? Let's think about what that means. Delta phi over delta t is the rate of change of the magnetic flux divided by the time over which it changes. Okay? So, if I have a current loop, for example, let me just draw a loop right here, and there's a magnetic field that is directed downward, and let's just say that it's increasing in time. This loop has an area A, and this magnetic field has strength B. Therefore, the flux, phi, we've already learned, is equal to B times A. The magnetic field strength times the area of the loop A. That's called the magnetic flux. Therefore, this delta phi up here means a change in magnetic flux. How much did it change in time delta t? So if it changed by 50%, there's some value in units by which it increases, delta phi, and there's also some value in units, notably seconds, for the time that it takes to do that. So if the flux in that loop, the flux, not necessarily the field, because the flux is the field times the area, and the change is either positive or negative depending on whether the magnetic field strength across that area is increasing or decreasing. Okay, so delta phi then is a change in the magnetic flux over that loop. Delta t is the time over which that change occurs. Remember, if there's no change in flux, if the flux is constant, then there is no induced EMF. Faraday noticed that it was only when fields change, when the flux changes in time, will there be an induced EMF. And now we've come to learn that the EMF is in fact the fraction delta phi over delta t, or in words, the rate of change of the magnetic flux in time. And the direction of the EMF is such as to drive an induced current in the direction given by Lenz's law, meaning that that induced current will produce its own magnetic field, which will oppose the change that's producing it in the first place. Okay, so what happens when we add a number of coils together, a number of turns, or a number of loops together? So if we put together n loops, and each loop experiences flux delta phi over time delta t, then the EMF is going to be equal to the ratio, the rate of change of the magnetic flux times the number of loops. And that makes sense. If there's 3 loops in the coil, then you're going to experience 3 times the EMF, because each loop is going to experience EMF delta phi over delta t. And think of those loops as little batteries. And so if I now have 3 loops, I connect the batteries in series. One has EMF delta phi over t. The next one has an additional delta phi over t EMF. And the final one has a third delta phi over delta t EMF. So it's like stacking up 3 batteries together, or in this particular case, n batteries, where each one has an EMF which is equal to the rate of change of the magnetic flux. Okay, let's consider a different situation where the effects of the induced electromagnetic field can be seen. Here we have a sheet of metal that is situated between 2 poles of a magnet. The magnetic field points down, as you can see by the blue arrows. Now let's imagine what happens when we pull that sheet out of that region to the right. Let's look at this loop on the right side here first. It has an area A, and you notice that it does have a net or non-zero magnetic flux, because there are some field lines that poke through that loop. But as the sheet is pulled to the right, notice that that loop will leave the field and therefore experience a decreasing magnetic flux. It's going to be a number that decreases in time to 0. And therefore, since it's a changing magnetic flux in that region, it will induce an electromagnetic field, an EMF, a voltage loop that will drive current. And in this particular case, it can drive current because it's a metal sheet. And so what happens then is that it's going to establish what are effectively circular currents in the metal. These are called eddy currents, and we'll look at the shape and direction of them in just a moment. So just to summarize, that loop on the right is going to leave the field and experience a decreasing magnetic flux, and therefore the EMF that it produces is going to drive currents. The left loop also has net magnetic flux, non-zero magnetic flux, and as the sheet is pulled to the right, notice that that loop enters more of the field. In other words, it has an increasing magnetic flux. So let's look at what those the currents look like that are produced by the induced EMF. On the right side, we said that this loop here had a decreasing flux, and therefore the direction of current is going to be such that the magnetic field it produces is going to oppose the change that produced it. Notice the change that produced it was a decreasing magnetic field, and so it's going to try and it's going to produce currents that have a magnetic field pointing down that will support the field as it weakens to try and oppose that weakening trend. The loop on the left, and therefore you can see that the loop, the current here, is directed in such a way when you use your right hand and curl your fingers along the direction of the current, you find that the magnetic field it produces is in fact directed downward. The loop on the left experiences an increasing magnetic flux in time, and therefore it's going to produce a B field that opposes that. It's going to produce a B field pointing up to oppose the increase of the field pointing down. And by the right-hand rule, you see that this eddy current on the left, which is counterclockwise as seen from above, produces a magnetic field pointing up. These are eddy currents. They're very common in metals where there are magnets moving around in the vicinity. You may also recognize the term as it's applied to rivers. A river can have eddy currents on the side when there's a small indentation, for example, in the bank to produce a small bay. And as the water flows down the river, there can be established eddy currents, which are circular currents in those side bays. And it's part of the result of fluid dynamics. So eddy currents exist in river flow, and they also exist in metal when the metal in which the electrons are situated experiences a change in magnetic flux.